Thank you very much, and thank you for the kind invitation to this wonderful workshop. So I will not be talking about sparsity. Sorry to disappoint. I would like to talk about problems that are called usually graph isomorphisms in the mathematical community and graph matching in the applied community. So if you look at these two graphs, despite the fact that they have different embeddings and despite the fact that the vertices are numbered differently, they share the same structure. So if you look at the adjacency information, it will be the same. So you can find an adjacency preserving bijection between the graphs, which is called exactly an isomorphism. So basically, I will be talking about undirected graphs, possibly weighted, and they will be represented by again, weighted adjacency matrices, symmetric because the graphs are undirected, A and B. And I will consider two problems. One problem is the exact matching problem. I would like to determine whether the two graphs are isomorphic, and in case they are, I would like to find an isomorphism relating between them. And the superset of this problem is an inexact graph matching. In this case, even if the graphs are not isomorphic, I would be interested in finding some best adjacency preserving bijection between the graphs that will be called some sort of an approximate isomorphism. Now, this problem can be written as an optimization problem with minimizing the norm of some norm of disagreement of the adjacency over all n by n permutation matrices, and because in particular the L2 norm or many other norms are invariant to permutations, we can actually make the function under the norm a linear function in pi in this permutation matrix that we are looking for. This problem is still, of course, is very ugly because the feasible set is utterly non-convex. Now, actually, it's a curious fact that this problem belongs to NP, but it is not known to belong either to P or to NP complete problems. Actually, if P is not equal to NP, it will occupy an intermediate complexity class between P and NP. Still, it is a hard problem to solve in this form. There is a wealth of literature in the graph theoretical community that I'm not going to cite. Hopefully, nobody gets offended. But the overwhelming majority of works in this field actually were done from the combinatorial perspective, and some works were done from the convex optimization or continuous optimization perspective. So one of the powerful and useful techniques that is used in the applied community is a convex relaxation of this matching problem. So if you look at the feasible set of this optimization problem, actually, by taking the convex hull of this set of permutation matrices, you obtain what is called the Birkhoff polytope, or the space of doubly stochastic matrices, which is a convex set. And then the problem becomes a quadratic program. Okay? Of course, the solution of this problem is not guaranteed to be a permutation anymore. It would be a doubly stochastic matrix, but it is not guaranteed to be a valid permutation matrix. So you need an additional step in which you project the solution of this relaxed problem onto the set of permutations. And there are multiple ways of doing so. I'm not saying that the one that I will consider here is the best, but it is simple. For example, you can consider the orthogonal projection of the solution onto the permutation set, and simple manipulations actually will show that this will be a simple linear assignment problem that can be solved in polynomial time using what is called the Hungarian algorithm, or can be formulated as a linear program. Okay, so basically these two steps, one is getting the solution of the relaxation P star, and then getting this pi hat, the projected solution of the relaxed problem. So as a result, you get a permutation matrix, and of course, the question is, like in any relaxation, what is the relation of what you're getting here to the solution of the original unrelaxed problem? Well, obviously, the solution of the original problem is a solution of the relaxation because it has a bigger feasible set. The converse might not be true because you might get some solution which is not a permutation matrix. You project it back, and unfortunately, it may fall into a Voronoi cell of a permutation matrix that is not an isomorphism. And to my surprise, when I got interested in this problem, actually I tried to find what is known about the relation of these two matrices, and it appears that quite little is known. So these techniques work; they work quite well, but it is not clear when exactly they work and when they would fail. So what I will show you is there are a few quite elementary results, but I think they are interesting. Maybe even the questions they lead to are even more interesting than the results themselves. So what I will consider is an even bigger relaxation than what is typically done by basically removing one set of these affine constraints and leaving just these constraints, and also removing the non-negativity constraints. So basically, as the result, we have an optimization problem with the convex polytope replaced by a bigger affine set. So it has n non-overlapping equality constraints and no inequality constraints anymore. And the practical consequence of this is that you can actually solve this problem by solving a linear system of equations that I will show you in a minute. So it's a bigger relaxation. What I will show you is that this relaxation actually is equivalent to the original problem on a particular class of graphs that I will call friendly. So the characterization of these graphs is not combinatorial. It is actually a spectral characterization, but spectral not in the sense of what is typically understood by spectral characterization in graph theory. I will consider the spectrum of the adjacency matrix itself and not of the Laplacian. So I will say that a graph, an undirected graph, is friendly if its adjacency matrix has a simple spectrum, meaning no non-trivial multiplicities of the eigenvalues, and also no eigenvectors are orthogonal to the constant vector, which, for example, excludes all regular graphs that have constant eigenvectors. Now, it is very easy to show. I will not show it to you, but it's really trivial to show that friendly graphs are necessarily asymmetric. Asymmetric in the sense that they have no non-trivial automorphisms, self-isomorphism of the graph. And the converse is not true. Again, you can think of a regular asymmetric graph, but don't kill me for this statement. Sort of, if you randomize a graph, this would be quite a rare situation to encounter something that is so regular and yet asymmetric. So basically, maybe if I have time, I will get back to this claim about random graphs. But basically, sort of many graphs are supposed to be friendly because having some degenerate eigenspaces is usually related to symmetry, to some regularity, which if you randomize a graph, is quite rare. So the first result I'm going to show you is quite straightforward. It basically claims that if we have two friendly and isomorphic graphs, then the relaxation will return exactly the unique isomorphism that relates between them. And of course, it will survive under the projection. It will remain the same. And basically, after the projection, you will get again exactly the same isomorphism. Now, checking that the graphs are isomorphic is hard. That's why you're solving a relaxed version of the problem. On the other hand, checking friendliness is easy because it's a spectral property. It's easy to verify. So what you would do in practice is verify friendliness and then solve the relaxation. If you get objective equals 0, then the theorem guarantees you that what you found is the exact isomorphism relating between the two graphs. And if you solve the relaxation and you found objective bigger than 0, then the theorem guarantees you that the graphs cannot be isomorphic. Okay? Now, I will show you why this happens. I think it will be important to see this linear system. So let's assume that we have two graphs, two friendly graphs, B and A, related to B through this isomorphism pi star. And what we are interested in is solving this convex quadratic program, which of course has a global minimizer pi star, right? So what remains to show here is that this minimizer is unique. Now, I would like to get rid of this matrix A by substituting this expression instead. Okay? And now I will use the fact that the L2 norm is invariant to permutation, so I will multiply everything by pi star transpose from the right. Permutation matrix is orthogonal, so I will get this. And I will also use the fact that I can permute the vector of 1s arbitrarily, and I will still get a vector of 1s, so I will put pi star transpose here. So basically, I created a new equivalent problem. I will call this p pi star transpose q. And again, this is a convex program. It has a minimizer. Q equals identity. So if I show that this minimizer is unique, it will automatically mean that the minimizer of the original problem that I can actually formulate and solve will be also unique. Okay? And here it's quite easy to see how to get this condition. I will write down the first order optimality conditions with this vector of Lagrange multipliers. And I will translate it into the eigenbasis of the adjacency matrix B that I will call U. Okay, so simple algebraic manipulations will lead me to this equation where F is the representation of the solution in the eigenbasis of B. Gamma is the representation of the Lagrange multipliers in this basis, and V are the projections of the eigenvectors on the constant vector. Okay, so this is our equation, and in coordinates it can be written like this. Now, if I consider the diagonal entries of this system, so in the diagonal entries, of course, the first term will vanish, and I will have Vi gamma I equals 0. Now, remember, however, that the Vi's are the projections of the eigenvectors on the constant vector, and we know that because the graph is friendly, they are non-zeros. Okay? So this automatically means that all the gamma i's are 0, so we can eliminate the second term from the system. Okay, when we are left with these off-diagonal terms. Now, friendliness again implies simple spectrum. It means that this constant will be necessarily non-zero for every off-diagonal entry of this system, and this means basically that F is a diagonal matrix. Okay. Now, if F is a diagonal matrix, we add another set of equations coming from the constraint that Q has rows summing to 1. So it means basically that Fv equals V for a vector with non-zero entries. And the only case this can happen is if F is the identity matrix, right? And if F is the identity matrix, then Q, the solution of the problem, is also an identity matrix. So we showed basically that that our minimizer is unique. Okay, and this, of course, completes the proof. Now, we can readily extend this result to the inexact setting by demanding a slightly stricter conditions on the friendliness of the graph. So instead of assuming simple spectrum, I will assume some lower bound on the spectral gap, and I will assume some lower bound on the angle between the eigenvectors and the constant vector. So I will call these bounds delta and epsilon. And if we are now given two graphs that possess this stronger friendly property, and I will assume that the graphs are no more exactly isomorphic, but they are rho isomorphic in the sense that there exists a permutation matrix that has an adjacency disagreement smaller than rho. Then basically, by using regular perturbation analysis, I can show that I will still have a full rank system, and I will solve it. The solution will not change from the unperturbed solution of the original system by more than 1/2 in the L infinity norm. So if I show this, a simple thresholding of the solution will still give me the exact permutation matrix that I started with. And of course, this analysis is extremely crude. I'm sure that if we analyze it better, we can get a better bound here. So here there is a bound on this rho in terms of epsilon and delta. It is something not particularly insightful. It depends on delta squared, epsilon to the power of 4, also on inversely proportional to the graph size to the power of 1.5, something like that. But basically, it means that this convex relaxation is stable if you allow a stronger friendliness property. Now, again, as before, I'm going to check this strong friendliness property and then solve the relaxation. If the result is smaller than this bound, I have a guarantee that what I found is the globally optimal approximate isomorphism. And if I get something that is bigger than this constant, then I'm guaranteed that the graphs cannot be more isomorphic than this constant rho. Okay? And this is an empirical validation of this result. So I took 1,000 graphs with this strong friendly property, and I added to them different levels of random noise to the adjacency matrices. And to show them on the same axis, I'm normalizing the noise by this bound that depends on each graph. So if this ratio is smaller than 1, then the conditions of the theorem hold, and the empirical success rate is 100%. When noise exceeds this number, we are getting failures. Now, when the noise is very strong, of course, this experiment is not fair because we might create new better isomorphisms that we cannot actually know that they were created, because finding them is as difficult as solving the original unrelaxed problem. Okay? So in the time that remains, I would like to say a few words about the unfriendly situation. What happens when the graphs are unfriendly? Why, basically, we saw that friendliness was necessary to get full rank in the KKT conditions. So when the graphs are unfriendly, we will have a degenerate system. So let's see what happens in this case. So in case of unfriendly graphs, there will be no more simple spectrum. It means that the eigenspaces will have non-trivial multiplicities. So let's say we have d such non-simple eigenspaces. Each one will have multiplicity mi plus 1. And let's denote by a constant m, basically the degree to which the eigenspaces are non-simple. This will be the sum of these mi's. Of course, if m equals 0, it means that the eigenspaces are simple. Now, the notion of eigenvectors, of course, in this case is no more well-defined. We can arbitrarily rotate an eigenbasis. So let's assume that in case we get an eigenvector that is orthogonal to a constant vector, we will rotate the basis in such a way that it will be no more orthogonal unless the entire eigenspace is orthogonal. In that case, I will call such a space hostile. And sorry for inventing these terms. So we have an unfriendly graph with hostile eigenspaces. But hostile eigenspaces will be those orthogonal to the constant vector. And of course, other eigenspaces will be non-hostile. Okay, so let's call the number of the hostile eigenspaces by k, and the degree of unfriendliness of our graph will be m plus k. Okay? So currently it's just an arbitrary number. The graph is friendly if this degree is 0. But what happens is that the KKT system will be exactly m plus k rank deficient. So basically, this degree actually tells us the dimension of the solution space of our relaxation. And of course, once we have an unfriendly graph, this is exactly where multiple solutions come from. And I said we might get problems with projecting one of such solutions back because it might fall into a wrong Voronoi cell and give us non-isomorphism, even if the graphs are isomorphic. Okay? So basically, I don't know what to do with this further, but what is typically done in applications, you introduce some side information to the isomorphism, to the matching problem, in order to disambiguate these multiple solutions. Usually they come from symmetries, so you want to somehow break the symmetry of the graph, introduce some additional information that will disambiguate this symmetry, and there are two standard ways of introducing this side information. One way is what is known as seeds, or knowingly corresponding functions. So assume that I have a function on the graph A and the corresponding function on the graph B. So I will denote these functions as column vectors of dimension n. Let's say we have q such functions. In the trivial setting, these would be just indicator functions of corresponding graph vertices. Okay, but they could be more general functions in the most general setting. So this is one way of introducing side information into the matching problem. Another way is by specifying vertex-wise attributes. So I will assign to each vertex a q-dimensional vector that will contain some additional information, and hopefully it will disambiguate the symmetries or the ambiguities in the multiple set of in the set of multiple permutation matrices that preserve adjacency information alone. So basically, you can think of this matrix C and this matrix D either as seeds if you consider its columns, or as attributes if you consider its rows, and you want these matrices C and D to select out of all possible isomorphisms some preferred isomorphism. Okay? So I will assume that this situation happens, and I will inject this side information into the convex relaxation by adding this term. You can think of it either as soft constraints on seeds, basically on known correspondence between seeds, or as a penalty on attribute disagreement. Okay, so either view is fine. And if you look again at the KKT conditions, basically what will happen is that this term contributes to these two terms in the first order optimality. Now, if you translate this system of equations back into the eigenbasis of B, as we did before, basically it will be the same equation that we had before, plus this term that is basically a positive semi-definite matrix, D transpose, projected onto the eigenbasis of the adjacency matrix. And meaning that this term actually will increase the rank of the system in general. So now you can ask the question, how do you construct the matrices C and D in such a way that they will fill in those missing equations in the non-simple eigenspaces of the adjacency? So you want to add a minimum number of seeds, which is m plus k, to create those missing equations. And actually, this can lead to constructive conditions that I summarize here. There will be a slightly different treatment of hostile and non-hostile eigenspaces. For hostile eigenspaces, you need to add one more equation. And then you again get a full rank system for any mu bigger than 0, meaning that again you will have a unique solution. Okay, and this unique solution for exact graph matching will be exactly the permutation you are looking for. Okay. Now, this is again an empirical evidence. So I took 1,000 symmetric graphs with different number of automorphisms of symmetries, and I'm solving this seeded convex relaxation problem, this one, with different number of seeds or attributes selected according to the conditions of this theorem. And I'm dividing the number of seeds by again, this constant m plus k in order to be able to compare the outcomes on the same axis. So if this ratio is 1, I'm adding exactly the number of seeds that is sufficient from the standpoint of this theorem to disambiguate the symmetries completely. And indeed, you see that in that case, the empirical success rate goes to 100%. Okay. Now, what is quite remarkable is that we could actually do with a stronger relaxation than what is done usually in practice. And the question, of course, is what did we lose? Can we get a wider class of graphs that on which we can guarantee equivalence of the relaxed and unrelaxed problems if we add some of these constraints back? And actually, there is an answer coming from a PhD thesis of Marcello Fiori that shows that if you put these constraints back, you can actually increase the class of graphs on which this equivalence will hold by replacing this non-orthogonality of the eigenvectors to the constant vector by some less stringent condition that is related to the number of 0 entries in the eigenvector, which is quite an interesting condition. And by the way, this is where sparsity comes into play if you wanted to hear about sparsity. But this is the only the only connection to sparsity I can imagine. So I don't know what is the physical interpretation of these number of zero crossings of the eigenvector. Okay. Now another thing that we didn't use in this treatment, which was, as I said, elementary, we didn't use any geometric properties of the adjacency matrices. For example, in many applications, the graphs represent some nice, smooth, say, low-dimensional manifolds, maybe with bounded curvature. So let's say we have adjacencies representing some pairwise distances in some nice metric space. Can we actually use this information? Can we use the information that our space is smooth? So not every permutation is allowed. We want nearby points to be mapped to nearby points, for example. So can we actually incorporate this prior knowledge to make stronger statements about the equivalence of the convex relaxation? Also, another thing that I don't have an answer to, but I think it would be interesting to think in this direction. Basically, the problem with the relaxation, the cases when relaxation fails, are due to symmetries. On the other hand, I don't want to answer the question whether symmetric graphs are rare or not, because it depends on the distribution. If you talk about random graphs, but let's say we are given a symmetric graph, and a statement that can be quite certainly made is that if you introduce random noise to this graph, with very high probability it will become friendly again. So if you add noise to the graph, you break the symmetry. So the question is, can you construct noise in such a way that on one hand it will break the symmetry and make the graph friendly again, so the relaxation will work, but it will be not strong enough in order to make the graphs too distinct in order for the bound not to apply anymore. So I don't have an answer to this question, but it would be very interesting to try addressing it, in my opinion. Also, another thing that sometimes is interesting, for example, can you enumerate all the isomorphisms or all the automorphisms of a graph? Can you enumerate, can you construct its automorphism group, its symmetry group? And the question is, of course, by considering the null space of that KKT system, can you actually come up with the structure of the symmetry group? How does it manifest itself from this null space? And finally, something that would be, in my opinion, extremely interesting is to find a combinatorial characterization of these spectral properties, like friendliness and strong friendliness, that currently are purely spectral, and it is not clear what is the combinatorial equivalent of these properties. In particular, what is the combinatorial equivalent of demanding this non-orthogonality to the constant vector? Okay, so I will stop here. If you have any questions, I will be happy to answer. Thank you.
So we have time for a few questions for Alex.
Mine is probably silly. If I did not misunderstand your questions, the relaxation space. So I would assume people know the tightest relaxation to these permutation matrices. Is that correct?
Yes, of course. The tightest.
Is it the doubly stochastic?
Yeah, exactly. The Birchhoff polytope. It's exactly the tightest. It's the convex hull of the permutation.
Is it the tightest relaxation, yes, or it's the
It's the tightest convex relaxation.
Okay. So there is. Okay. So I see. Oh, okay. Then it is that.
So basically, we dropped some of these constraints. We increased that space, and still you can, at least on a quite wide family of graphs, you can show that that you get equivalence by putting some of these constraints back. You can increase the family of these graphs.
And how about the partial permutation matrices?
Okay. So well, this is, of course, this is we didn't explore this problem, but basically what you're saying is that you have some non-bijection, right? Some partial correspondence between graphs. Mm-hmm. So first of all, the original problem would be NP complete, but I don't know if there are any results. Something that is definitely very interesting to consider.
Okay.
Any more questions? So if not, let's thank Alex again.